The silicon industry forms the indispensable backbone of our modern digital world. Without its foundational work, the technological advancements we now take for granted would be impossible. This sector is primarily responsible for the creation of microchips, miniature marvels of engineering that drive nearly every electronic device. These tiny integrated circuits are far more than just components. They are the literal brains of technology. They power the ubiquitous smartphones in our pockets, the powerful computers we use for work and leisure, and even the sophisticated systems within modern automobiles. Beyond consumer electronics, silicon chips are critical to medical devices, aerospace technology, and advanced industrial machinery. This is a profoundly complex and highly specialized sector, characterized by intricate processes and enormous capital expenditure. Its scope extends from the initial extraction of raw materials deep within the earth to the final, highly precise manufacturing of integrated circuits. Each step requires meticulous control and cutting-edge innovation. Understanding the silicon industry is not just about appreciating its technological output. It is about recognizing the fundamental engine behind global innovation and economic growth. The journey from a simple rock to a sophisticated computer chip represents one of humanity's most remarkable engineering feats. At the heart of the silicon industry's foundation lies its core reliance on a single element, silicon itself. This abundant material is not merely a component. It possesses unique properties as a semiconductor, making it ideal for controlling electrical currents. This characteristic is precisely what allows for the complex operations within microchips. Silicon is remarkably common, constituting a significant portion of the Earth's crust. Its most prevalent form is found in sand, particularly in quartz and silica. This widespread availability is a significant advantage, but extracting usable silicon for electronics is far from a simple task. The raw material must undergo an essential and rigorous purification process. This multi-stage procedure is designed to achieve an extraordinarily high level of purity, often reaching 99.999999% or even higher. Any impurities, even at trace levels, can severely impair the performance and reliability of the final microchips. This critical stage is frequently referred to as silicon refining or the polysilicon stage. Here, metallurgical-grade silicon is converted into electronic-grade silicon, a material almost entirely free of contaminants. The meticulous control of this purification is absolutely crucial for ensuring product performance and long-term reliability in sensitive electronic devices. Without this extreme purity, transistors would not function consistently, leading to system failures and diminished capabilities. Once ultra-pure silicon is obtained, the next critical step involves the formation of single-crystal silicon wafers. These thin, circular slices serve as the foundational canvases upon which microchips are meticulously built. Creating a flawless single crystal requires highly controlled conditions to ensure uniformity and structural integrity. The fabrication of microchips on these wafers involves a complex series of processing steps, often numbering in the hundreds. Each stage is performed with incredible precision, often at the nanometer scale, which is billions of a meter. These steps include techniques like deposition, etching, and most critically, photolithography. Photolithography is arguably the most vital step in the entire microchip fabrication process. It uses specialized light sources to transfer intricate circuit designs onto the silicon wafer. Think of it like a highly advanced form of photography, where ultraviolet light projects patterns through a mask onto a photosensitive material coated on the wafer. This process allows for the achievement of incredible precision, enabling the creation of features smaller than the wavelength of visible light itself. Following photolithography, etching processes remove unwanted material, while deposition techniques add new layers. These cycles are repeated numerous times, building up the complex architecture layer by layer. Ultimately, these intricate patterns lead to the creation of billions of transistors and other interconnected components. These microscopic switches are the fundamental building blocks of digital logic, enabling microchips to perform calculations, store data, and execute complex commands with unparalleled speed and efficiency. The entire sequence is a testament to humanity's ability to engineer at the atomic level. The silicon industry is characterized by its highly specialized nature and its immense capital intensity. Building and operating the facilities required for chip manufacturing demands colossal investments. This reality shapes the entire structure of the industry, fostering an environment of continuous innovation and fierce competition. Leading players in this global industry include household names like Intel, renowned for its processor designs and manufacturing capabilities. Taiwan Semiconductor Manufacturing Company, or TSMC, stands as the world's largest dedicated independent semiconductor foundry, producing chips for countless other companies. Samsung, a diversified technology giant, also holds a significant position in memory and logic chip manufacturing. These companies, and others like them, commit significant investments across various fronts. Research and development, or R&D, absorbs billions annually as companies strive for smaller, faster, and more efficient designs. This relentless pursuit of innovation is essential to staying competitive. Crucially, building and maintaining state-of-the-art fabrication facilities known as fabs requires monumental financial outlay. A single leading-edge fab can cost tens of billions of dollars to construct and equip. These facilities are not just expensive, they are incredibly complex to operate. Fabs are meticulously designed to be among the cleanest environments on Earth, far cleaner than surgical operating rooms. They operate under rigorously controlled conditions to prevent even the tiniest speck of dust from contaminating sensitive silicon wafers. Such contamination could ruin an entire batch of expensive chips, underscoring the absolute necessity of precision and control in every aspect of manufacturing. Furthermore, attracting and retaining a workforce of highly skilled engineers, scientists, and technicians is another significant investment for these leading companies. The silicon industry is defined by its constant, relentless evolution, a pace of change almost unparalleled in other sectors. This dynamic advancement is largely driven by a concept known as Moore's Law, first proposed by Intel co-founder Gordon Moore. This observation predicted that the number of transistors on an integrated circuit would double approximately every 2 years. For decades, this law has largely held true, driving unprecedented miniaturization and a continuous increase in processing performance. The ability to pack more components onto a smaller space has fueled every generation of technological advancement, from early personal computers to today's artificial intelligence accelerators. This progression is not merely about density, it's about enhanced power, efficiency, and capability. This remarkable evolution is a result of continuous innovations across several key areas. Breakthroughs in material science have introduced new compounds and structures that improve electrical properties and thermal management. Manufacturing techniques have been refined to engrave ever finer details and build more complex three-dimensional chip architectures. Moreover, advancements in chip design methodologies have allowed engineers to create increasingly sophisticated and specialized processors for diverse applications. Despite this impressive trajectory, the silicon industry faces significant challenges. The sheer cost of research and development continues to escalate, pushing the boundaries of economic viability for smaller players. The complexity of manufacturing has reached astonishing levels, requiring specialized knowledge and equipment that few entities possess. Furthermore, the industry is increasingly grappling with geopolitical implications, particularly concerning global supply chains. The concentration of advanced manufacturing capabilities in specific regions has created vulnerabilities, as starkly highlighted by recent global chip shortages. These shortages impacted industries worldwide, from automotive to consumer electronics, underscoring the critical nature of a stable and resilient silicon supply. Ensuring security and diversification within these supply chains has become a paramount concern for governments and corporations alike. In summary, the silicon industry stands as a vital and intensely dynamic sector, perpetually at the forefront of technological innovation. It is an industry that, though often unseen, underpins nearly every facet of our digital existence. Its foundational role makes it essential for the continued advancement of technology, shaping the world we live in and the world yet to come. From the sand of our beaches to the complex integrated circuits within our most advanced machines, the journey of silicon illustrates human ingenuity at its peak. The constant drive for smaller, faster, and more efficient components is not just an engineering challenge. It is a fundamental societal imperative. The pervasive influence of this industry makes it a critical component of the modern world's infrastructure and economy. For students embarking on their careers, understanding this industry opens doors to countless opportunities in engineering, science, and business. For investors, recognizing its unique characteristics, its cyclical nature, and its strategic importance is crucial for informed decision-making. The silicon industry is more than just a market. It is a strategic asset. Therefore, a comprehensive understanding of the silicon industry is not merely academic. It is absolutely crucial for comprehending the broader technological landscape, anticipating future trends, and appreciating the intricate web of innovation that connects us all. The future of technology, indeed the future of our digital civilization, remains intrinsically tied to the ongoing evolution and success of the silicon industry.